thank you so much for organizing this seminar. It's been really great to attend, and thanks for the invitation to speak today. So I'm going to talk about work that was joined with Jingsheng Xu, graduate student at the University of Wisconsin-Madison. He's fantastic. And then the work that I'm going to talk about is available on arXiv. So as you know, I'm interested in explicit phylogenetic networks. There are extensions of trees that have, what trees don't have are hybrid nodes. There are nodes that represent reticulation events. And so in explicit phylogenetic networks, each node represents an actual ancestral population. And then hybrid nodes would receive genetic material from two parents. So we need, I'm interested in metric networks where we do have information about the proportion of genes that was received from either parent by the hybrid node. And so this, I'm not showing here, but this edge would have to have an inheritance 1 minus gamma 1, because these are properties that need to sum up to 1. And for these metric networks also we have edge lengths. So each edge hybrid and tree edges have a length that needs to be non-negative. Also here, I'm not restricting the networks to be binary. They could be non-binary. So they could have 2 or more parents for the hybrid nodes. And any node can have 2 or more descendants. And okay, so these are explicit networks. And then, as you know, I've been interested in networks for some time. And what's frustrating in some of the previous work I've done is that they're really hard to infer. The computations are really heavy. And so that's why I got interested in maybe using distances for networks. Maybe there could be methods that use distances and are much faster than other methods. But then the question is, distances provide very low information. And so maybe there's not much we can identify from these distances. So that's the question I want to tackle here is, what is it that we can identify about the networks when all we have are average distances? So now I'm going to talk about what average distance is. And so in a network, if I consider 2 leaves, then I might be interested in the distance between these 2 leaves. And to define this distance, I'm looking at the displayed trees that I can get from the network. And so by this, I mean, to get a tree, one way to get a tree is to remove, for each hybrid node, remove one of the 2 parents and keep only one. So I'm going to keep this parent, for example, and remove this one. And maybe I can keep this one and remove this one. And if I do so, then I get this displayed tree. And then on the tree, there's a unique path between the 2 leaves. And I can look at the distance between these 2 leaves on this path. And then an average distance would be the average of these distances over all the displayed trees that I can have. And the average is using the weights of each displayed tree, which is just the property of getting the tree, as I mentioned before. And so this is meant to capture the average distance if I take a site at random. If I take a site at random or a gene at random, if we have one of these displayed trees. Okay. So this is really a technical definition. It's not linked to a model of getting data. And I'm not saying what the edge lengths represent. They could be defined in various ways based on various models, and I'm not worried about this here. Also, if you have any, if you want to interrupt me at any time, feel free. All right, so, oh, it shut off my, you know what I'm gonna do this so you can see me. But I don't know if this is going to be captured. Anyway. So previous work on this dates back to about 10 years ago, when Stephen Wilson looked at this question when the topology is completely known. And can we identify the parameters? And for the most part, the answer was yes. except for some assumptions that needed to be made. And then a year later, looking at the same question, but now can we identify the topology? And then the answer was really much more complicated. And the answer was yes, if really there's only one reticulation, and then with extra assumptions that were fairly technical. And then some years later, Andrew Francis and Mike Steele looked at the question, when is it that, in terms of average distances, when is it that a network is equivalent to a tree, meaning have the same average distances? And they showed that mostly that network needs to be mostly tree-like, except for some reticulations here and there, based on the assumptions that they made on their networks. And there's been a ton of work actually using other kinds of distances, so mostly sets of distances or shortest distances, so other results in that area that seems to be stronger. Sets of distances are really a lot more rich information. And then very recently, Elizabeth Orman and Hector Baños and John Rhodes had a preprint on a distance that seems to be very, very close to the log distance. So this is really using data. And they showed that for the most part, level 1 networks are identifiable. So I'm going to show you some results that really focus on local features of the network and some global features of the networks. And I will have a lot of bad news and then some good news. So for the bad news, something that you might say, oh, duh, of course, is that the root is not identifiable. And by this, I mean that the least stable ancestor, that's the node here, such that any path from the root to any leaf has to go through it. So this least stable ancestor and anything that's above is not identifiable. So this is well known for trees, but interestingly, I didn't find it clarified in previous work, and there were other assumptions that were made in previous work. So then if the root is not identifiable, what we could potentially identify is the semi-directed network. So what this network is a network where we remove information about the root, we remove the root, and then we remove the direction of all the tree edges. So any hybrid edge that goes into a hybrid node, these edges are kept directed, their direction is known, and any other edge, their direction is forgotten. But because hybrid edge are kept directed and tree edge are not directed, we know who are the hybrid edges and we know who are the tree edges. And so therefore we know who are the hybrid nodes, because the hybrid nodes are the nodes such that there are incoming hybrid edges into them. So that's the semi-directed network that we hope could be identifiable. And a few more things about a semi-directed network is that what we showed is if I take a rooted network and then I consider the semi-rooted network I get from it, semi-directed, sorry, the up-down paths on this rooted network, they are the paths that I know I go up and then I go down. And I know I go up because all these edges are directed in the rooted network. And then I know I go down. These up-down paths are exactly the path here in the semi-directed network that don't have any V structure. And a V structure would be I go down and then up like a V through directed edges then. So obviously a path here that's up down doesn't have any V structure, but conversely, any path here that doesn't have any V structure does correspond to an up-down path here. So there, yeah. And so what that means is that really the up-down paths don't depend on the root, and so all the distances we can consider on our network don't depend on the root either. So this is an example network where I changed the root position. Instead of being here, I placed it there, right? And so here I have this edge would be cut into two, one tree edge and one hybrid edge. So that's one tree and one hybrid edge. And the up-down paths are going to be the same with the same length, right? And so what's still well-defined in the semi-directed network are all the up-down paths, and from there, all the sets of distances, and from there, the shortest and the average distance. Okay, another piece of bad news of things that are not identifiable are the edge lengths around a hybrid node. So if here we have a hybrid node, the edge of the child node and the edge of the parent nodes are not identifiable apart from each other. So what we showed is that if we take a network and then we construct a new network that is mostly the same except for the edges of the hybrid adjacent to a hybrid node in such a way that this stays constant, then all the average distances are going to stay the same for the two networks. And maybe you're going to tell me, oh, well, I'm not surprised. What's not surprising is when we zip this hybridization up here or down, in the sense that we decrease both of the parent edges by some constant and increase the child edge by some constant. So here we don't change the display trees. Display trees are gonna, if I go left, this length and that length are gonna be the same. But yeah, and so that's not so surprising. But there is a second degree of freedom, actually, that is sliding left or right, that reticulation. So not changing the child edge, but decreasing one and increasing the other of the parent edges. And if we have a polytomy here, then there's more degrees of freedom. So previous work really assumed that most of these hybrid edges had a length of 0 or some other assumptions. But this really lack of identifiability was not clarified. And so it would be good to consider for identifiability Ziptop networks, which are networks in which both of the hybrid edges or all of the hybrid edges have a length of 0. And it's really easy to make to transform a network to be Ziptop. We just need to increase the length of the child edge by whatever quantity is needed to keep that key quantity constant. And if we have a polytomy here, then we need to add an extra child edge to resolve that polytomy in some particular way.
Cécile, can
also,
I'm sorry,
yeah,
I'm taking advantage of your kind offer. Did you say that the networks were binary?
Not necessarily.
Okay, so when you zip up, if you had a third edge coming into the hybrid node, can you just explain what the zip up would do? Thank you.
Yeah, so if we zip up, if we had a third incoming here, that it would be hard to call this zipping up because we would need, no, it would remove a constancy to all of the 3 or 4 or all the parent edges, and then the average of what we take out would be that constant, and then we add this constant to the child. And so we can transform a network to zip it up completely. We can do this at any one node, and then we can do this at all nodes. So if we do this, let's say I zip up at H2, and then later it's zip up at H1, I'm unzipping H2, and so I have to re-zip up again at H2. But what we showed is whichever order we do this, we end up with the same Ziptop network. Okay, so then our revised goal is to identify a semi-directed Ziptop network. Okay, so more bad news, but this one is, in my opinion, more interesting, is swapping a very local feature without changing the global average distances. So consider a network that's semi-directed, and then consider a subgraph, let's call it A, within that network. And we assume that our subgraph is hybrid closed in the sense that if there is a hybrid edge that belongs in this subgraph, then all of its partners, this one, also have to belong in the graph, right? And then we're going to call delta A the the boundary of this subgraph. So these would be, and I denoted here as big black dots to say these are the boundary nodes. And this boundary would be any node in our subgraph that has links to outside of the subgraph within that bigger network. And if I don't have big dots here, I mean that these nodes are not part of the boundary. So what I mean is that there are no other edges that connect these nodes to the bigger network. All right. And so now we can consider swapping this subgraph by another one with the same boundary. So if in my network I had these other nodes, I want to keep those other edges, I want to keep them, but I can change what's inside. Right? And so we're going to consider another subgraph A tilde such that after the swapping, the bigger network is still a semi-directed network. And then we showed that there is some local properties that we can easily check on these subgraphs that if they're met, then the bigger networks before and after the swap have identical average distances. So overall, it won't change the distances. And then these properties are easy to check. They are about the weight of the paths between boundary nodes that staying within the subgraph. So in these examples, I can go from C to B within A with weight 1. And I have this path. It's all through 3 edges, the weight is 1. I cannot go this way because it has a V structure. And I cannot go that way, also has a V structure. And in this subgraph, the gamma between C and B is the same. I would go through this only, it has weight 1. All right. And in some examples, it's less than 1. And then it's the average distance between U and V conditional on staying within A. And so that would be looking at all the up-down paths, all the paths without any V structure that goes from a node to another node, staying within A, and looking at the distance of each path, and then taking the weighted average with the weights, and then normalizing by the weight of all these possible paths. And so if these two matrices are equal before and after the swap, then we prove that the average distances in the larger networks are equal. So this can have tons of applications, and I'm just going to show immediate applications. One would be if we have a blob of degree 2, so something like this, and I'm showing here an assumption that would be that the only boundary for this subgraph are A and B. This could be a blob, like a bi-connected component, or it could be within a larger blob. You know, there could be edges here and a hybridization, doesn't matter. Here gamma between A and B is 1, and the distance between A and B is whatever it is, so I can swap this by a single edge. And same thing for a blob of degree 3. So if I only have 3 boundary nodes, then I only have, here gamma is also 1 between each pair of boundary nodes, and I can always match the distances by distances on a small tree structure. So the blobs of degree 3 are not identifiable. These smaller structure within bigger blobs are not identifiable. Other examples, 3 cycles. They come in 2 flavors. A 3 cycle can be 2, so a hybrid node and the opposite edge is a tree edge, or a hybrid node and the opposite edge is a hybrid edge. And in both cases, we can swap this with something that's simpler. So here I can swap this with a tree-like structure. And here I have to consider these as boundary nodes. And I have to make the assumption that V doesn't have any other child edge because it's not supposed to be a boundary node. And then I can swap this with something simpler that has 1 fewer reticulation. And here's an example where, for example, between this node and that node, there are absolutely no paths within the subgraph. I cannot go through here, it's a V structure. I cannot go through there, it's a V structure, but that's okay. And then if we apply this recursively to a subgraph like this, where you have speciation and then gene flow in between the two species, we have a 3-cycle here that we can simplify. And then once we do this, we can simplify this other one and so forth. And so in the end, we just end up with a tree structure, subtree. So this seems like duh, but in fact, it's what biologists would be assuming to be the most common kind of reticulations, because after any speciation is never immediate, it's gradual. So we expect some kind of gene flow between the two incipient species. And also populations that are closely related should be more able to hybridize than populations that are distantly related. But in terms of average distances, it's absolutely invisible. And also, this examples relates to a paper by Andrew Francis and Mike Steele from 2015, where they showed that it's the only kind of reticulation you can see without, while for a network to still be tree-like in terms of average distances. Actually, I think that's here, when they consider a specific class of hybridization networks. And for a specific class of HGT networks, oh no, that was HGT networks before. For hybridization networks, the only reticulation that could be seen was near the root. And we can explain this really easily because the root is not identifiable. So when we remove it, we end up with a 3-cycle here. And a 3-cycle can be, is unidentifiable from a subtree. So really we end up with something that's tree-like. And the network that I started with at the beginning was looking like this. So when the root is not identifiable, we get a 3-cycle. We can simplify it, we get this, and then we see, oh my gosh, I have another 3-cycle here. I can simplify this again. So it's really easy to see that then this network has the same average distances as another tree. Okay, so another application of our swap result is that level 2 networks are not identifiable, and tree-child networks are not identifiable either. Actually, level 2 and tree-child networks are not identifiable. We just need to provide one counterexample, but that would be one where we can swap this subgraph by either this one or that one. And we can do so not necessarily for all parameters, all branch lengths, B's or T's or U's, but for a very large space. So definitely a set of parameters of measure, positive measure. So even if we wanted to have a generic result, level 2 wouldn't work and tree-child wouldn't work. So I think I'm done with bad news. We can move on to some good news. And so to get some good news, we wanted to get away from these blobs that can be swapped by other blobs. So we looked at the blob tree. So basically it's a tree structure of the network. So what do I mean by the blob tree? I'm looking at what we mean by blobs are the 2 edge connected components of the network, which means a connected component such that if I only remove one edge, I don't disconnect it. I have to remove 2 edges to disconnect it. And the nice thing about 2-edge connected components, these blobs, is that they partition the nodes. So all the nodes here would be in the same blob. All the nodes here would be in the same blob. And this node would be its own blob. This node would be its own blob, and so forth. And then we can construct a blob tree that has one node for each of the blob in the network. So this node would correspond to this blob. And then we connect the blobs that are connected originally by some edge in the network. And we get a tree doing so. And what's nice about this is that every edge in the blob tree corresponds exactly to a cut edge in the network. So a cut edge is an edge when I cut it, I disconnect the network. We could also consider blocks. So these are the bi-connected components. It's looking at nodes disconnecting instead of disconnecting by removing edges, we would be removing nodes. And considering a block cut tree, which would have extra nodes, extra edges, so it's not just that it's nice, but if our network is binary, the blobs or the blocks are the same, and we get the same tree. But for this particular example, the block cut tree, after we remove degree 2 nodes, we would have an extra edge here that corresponds to this cut node, and we have an edge here that corresponds to this cut node. So in a way, it separates the polytomies that are adjacent to the blobs. Okay, so if we're looking to identify the blob tree, you won't be surprised that I'm going to consider the 4-point condition. And so a split xy versus uv set to satisfy the 4-point condition if the sum of two distances xy plus uv is the smallest of the three that we can consider. So this is smaller than distance of xu plus yv or xv plus yu. And if these two are equal, right? And so on a tree, everybody knows it's true, it happens. And a split on the full taxon set would be said to satisfy the 4-point condition for any 4 taxa, 2 on one side and 2 on the other side, the 4-point condition is met. And so you won't be surprised that I'm going to look at all the splits that satisfy the 4-point condition for a given distance. And then we're going to refine that set of splits by keeping just the splits that don't conflict with any other splits in those that satisfy the 4-point condition. And this is to get rid of the splits that would resolve polytomies. And then because these don't conflict with each other pairwise, we know it's a standard result that they come from a unique tree. And we call this the split tree, the distance split tree. Okay, so we have a distance as an input. We get all these splits that satisfy the 4-point condition. We remove some of them if they conflict, and then we get a tree. Okay, so as you know, if we start from a tree such that any edge of length 0 has been contracted to create a polytomy, and then we get the distances from this tree, and we use these distances to get the splits, then we get back our tree. So it's a good candidate to get back the blob tree in a network. And indeed, what we showed is if we have a network that's semi-directed and with average distances d, if we make really easy assumptions that there's no degree 2 blob and that the cut edges have positive length, then our distance split tree is a blob tree. No, it's a refinement of the blob tree. So unfortunately, we could only prove that we get a refinement of the blob tree. But refinement cannot be avoided. And here is an example. That's a network that has 1 blob. So its blob tree is just a star. And for some choices of branch lengths and gammas, then actually the distance in this fit this tree exactly. And so in that case, the distance split tree will be that tree, that topology. So we conjecture, but we didn't prove it, that the distance split tree that is recovered by this method is actually the blob tree of some network that is not necessarily the network we started from, but a network that is indistinguishable from our original network based on average distances. And in fact, it's the case for level 1 network. So if we assume that our network N is of level 1, and we make the same small assumptions, it has no degree 2 blob, internal tree edges have positive lengths. So here, not just cut edges, but also any other internal tree edge, like these 3. Otherwise, contract them and create a polytomy. Then the distance split tree is a blob tree of a refinement of N. And this refinement is exactly when we separate the polytomies that are adjacent to the blobs. So If this is our starting network, our distance split tree would recover that. And this is n tilde. So finally, so this is a global feature of the network that would actually probably could help in working on divide and conquer methods, perhaps. So what about the full network? We know that we need to ask for a semi-directed network. We need to ask that it's be unzipped and no degree 2 blobs, no degree 3 blobs, and things like this. We know that the class of level 2 networks is too large. Tree-tri networks is a class that's too large. So we went with level 1 networks. And here, you know, it could tell a short story, but I'm going to go in some detail about the 4 cycles. But before this, I'm gonna say there are no 4 cycles, because then the story is really simple to state. So let's consider this class C5, where I can have 5 cycles, but no smaller. So it would be semi-directed networks, Ziptop, no degree 2 nodes, no 2 cycles, no 3 cycles, because we know they're never identifiable. That's a big assumption, it's level 1. That's a really small assumption. It's internal tree edges have positive length. Otherwise, just contract them and make polytomies. And that's another big assumption, no 4 cycles, but we'll get rid of it later. And then we showed that if our network is in this class, then the network is identifiable from average distances. So completely, including the parameters, the gammas and the branch lengths. So that's nice. And the gist to prove this is to prove it for summits. And then because we have the blob tree, put everything together. So the sunlets are really simple level 1 networks where we have 1 cycle and then external edges onto this cycle. And because we can identify the blob tree with this refinement, so it really helps us refine the polytomies, we can just select one of the taxa from each adjacent to each of these cut nodes, and then identify this cycle. And when we have 5 or more taxa, this node, when we ignore it, is the only one that gives us a tree structure. Now, any other one, if we have 5 or more taxa, if we remove that one, we don't get a tree structure. So that's the gist of the proof. Now, if we want to consider 4 cycles, that's more complicated, as we've seen this happening from other kinds of input data. So here I'm showing a 4 sunlet, because if we just need then to put things together, so we just need to consider small cycles. In this network, H is of hybrid origin. Here G is of hybrid origin, and here B is hybrid origin, and there will be a 4th one where it's A. Right. What they have in common is that they have the same circular ordering. So going this way, we go A, G, B, H, but it doesn't matter if we go around and where we start. That's the circular ordering. And we can identify this circular ordering from the distances. And it's in a way that's very similar to checking the 4-point condition. So if these 2 edge lengths here are strictly positive, then the 4-point condition is violated. And in the way in which it's violated tells us who are opposed and on diagonally placed. So AB should be on 2 different ends, and GH should be on 2 different ends if this sum is the largest of the 3 sums. So that's identifiable, the circular ordering. But basically that's it from average distances. Because if we take any distance on these 4 taxa, any, and we just identify which circular ordering gives, it's compatible with. And then we just need this to be satisfied for that distance to fit on this network here, where H is of hybrid origin. And this condition is really easy. If D is a metric that is necessarily less than 1, and this is also necessarily less than 1. So asking for the sum to be less or equal to 1 is not that much. And in fact, if we take any blob here, any, and we get distances from that network, and if this is not met, this condition is not met, we just increase that external edge and or increase that external edge to b, and this is met then, so provided that we increase these two external edges long enough. So really, this is really easy to satisfy. And in fact, it's if distances come from this network where G is of hybrid origin, this condition is satisfied. And so these two networks are never, ever identifiable from each other. Okay, so what we can identify, though, are these composite parameters. And the nice thing about these parameters is that I can define them without knowing who is of hybrid origin. I just need to know the circular ordering, and that's it. Not the exact topology. And then we can represent these composite parameters in a split network this way. And in a split network, we have two pairs of split edges. One pair is here. They represent only one thing. They only represent one split, AB separated from AH separated from GB. And so they only have one weight, and they are represented as parallel because they have the same length, they represent the same thing. And this other pair also represents just one split with one weight. And in a network like this, we read distances differently. We just go for the shortest distance. So the distance between A and G is read from here, and between A and B, it doesn't matter which path we take, this one or that one, they're considered equivalent and they have the same length. And these composite parameters capture everything we can know from distances. We have six distances, that's 6 parameters. The nice thing about these is that if we knew for some reason that H was of hybrid origin, then in fact, this mu hat G would be equal to this length mu G. And this mu hat H would be equal to that length mu H if this network is zipped up, completely zipped up. And then we would know that what we can recover from the distances, mu hat A and mu hat B, are overestimates of the true lengths. And then we would know that what we can recover about within the cycle are underestimates of the tree edge lengths. So it's a good representation of what we know. The thing is, we don't actually know who is of hybrid origin, who are the tree edges, but that's okay. So some examples where all these networks here are equivalent to each other, have in terms of having equal average distances. All of them have this representation as a split network. And this example is to show you that we don't actually know if there might be an external edge of length 0. It's possible that this edge here is of length 0, or it's possible that this one is of length 0. So in reality, we could have a polytomy here. We cannot tell from pairwise distances about polytomies adjacent to 4 cycles. Okay. So now for a bigger network, what we're going to do is consider a mixed representation of our network. What we do is any 4 cycle, like this one, we convert to a split network. For level 1 network, any larger cycle we leave as is. So in our mixed representation, we're going to get a network where some parts have the standard hybrid edges, standard tree edges. And then other parts will have 2 pairs of split edges. In a way, they look like tree edges because their gammas is 1, they are undirected, but they're also split edges are not the same. And then we are going to suppress degree 2 nodes, so if we might need to suppress these nodes later. So here is an example where we have a 5 cycle, we leave it as is. This is the 4 cycle, so we are going to replace this by split network, and then we're going to remove these degree 2 nodes. And then we need to define an average distance on this kind of network, and we're going to do the same as before. We are going to take a weighted average of all the paths that go between 2 tips, But now the paths are mixed UpDown path, and we're asking that they don't have any V structure, and any split segment needs to be of minimum length. So if I go from here to there, I cannot go here, it's a V structure, so I have to go that way, and then either this or this. And these two paths would be considered equivalent. And then we're going to consider only one path from each equivalence class. And then what we showed is, with this definition of distance, the mixed representation has exactly the same average distances as the original network. And then finally, we can consider the class of level 1 networks that are, as before, semi-directed, Ziptop, no degree 2 nodes, no 2 or 3 cycles. The biggest assumption here is it's level 1. It could have 4 cycles. And then for networks in this class, what we can identify is the mixed representation. That's what's identifiable from average distances. And it actually captures everything that's identifiable from average distances. Okay, so some take-home messages. I think there is value to study local and global features in a network. For local features, if we know that some things are not identifiable, and if we write software that is going to try to estimate a network based on this kind of data, we shouldn't try to have these local features in our networks. We should avoid them, because otherwise we're just not going to search efficiently. It doesn't mean that we're making assumptions. Like, for example, if we are constraining all the hybrid edges to have length 0, it doesn't mean that we assume they have length 0. It means that we just constrain them to have only one network from the equivalence class. And so I think it will take some work to explain to biologists that these are artificial constraints. They're not assumptions. And also, probably something that would help are tools to visualize the equivalence class of a given network. So tools maybe to interactively zip a reticulation up or down, or for example, or tools to interactively change the hybrid node in the 4 cycle. And then global features could be really useful if they can lead to new divide and conquer approaches to internetworks. And then there are lots of things that I love to do next. Level 1 is really a very small class of networks. It would be helpful to know what assumptions we need, what to make on the network to still get identifiability. What is a good larger class? So I just want to say this is work that I did with Jing Shang, and I want to thank Sebastian Rock for useful discussions, and John Fogg also for useful discussion for reading our preprints, and then acknowledge NSF funding. Thank you everyone for listening.